Hello everyone, I'm Dr. Nasreen Fathima, Associate Professor and Head Department of Computer Science and Design, ATME College of Engineering, Mysore, India. Today I'm here to give a presentation on my paper titled A Novel Intelligent Trust Computation for Securing Internet of Things Using Probability-Based Artificial Intelligence. My co-authors are Dr. M.S. Sunitha Patel, Associate Professor and Head Department of AI/ML, and Mr. Kiran B. So moving on to the introduction. Now coming to the overview of IoT and security challenges. With rapid growth in IoT devices in smart cities, securing these networks has become a critical challenge. Most of these huge networks are also susceptible to denial of service attacks because of the huge number of interconnected devices. Data security, ensuring privacy and protection of the vast data generated by these IoT devices is challenging, and attackers can exploit weak points across many devices. How AI can be used in enhancing IoT security? AI, artificial intelligence, can analyze large amount of IoT data, detect anomalies in this, and identify threats in real time. It allows proactive threat detection rather than relying on traditional reactive security measures. We discuss some of the existing systems, existing solutions which are based on AI. So here, various methods of machine learning, deep learning, machine learning models like support vector machines and decision trees are used for detecting of IoT attacks. Deep learning techniques like artificial neural networks and convolution networks also help in detecting advanced threats. Reinforcement learning can be applied for decision making in complex dynamic environments. We also have various cryptographic techniques such as the advanced encryption standard as well as the elliptic curve cryptography are common approaches used for IoT security. Challenges with these existing models. First issue is with scalability. AI models can be resource intensive and inefficient when deployed at large scale, due to which there is inconsistent performance. Ensuring uniform security across a wide range of heterogeneous IoT devices is difficult. Existing AI models tend to focus on accuracy but require significant computational power, making them unsuitable for resource constrained IoT devices. We see how some of these challenges can be overcome with the proposed system. So proposed study, here we propose a novel approach of trust computation via artificial intelligence and probability-based models. The study introduces a novel trust-based computation model for IoT security system. So here, the main contributions or the key factors here is a creation of a smart city region framework where IoT devices are divided into small regions for easy monitoring and security management. Reinforcement learning for decision making, it can be applied to improve decision making in detecting threats. New adversary detection mechanism introduces a model to detect unknown evolving threats in IoT networks. Combining these probability models with AI-based decision making and use of lightweight efficient algorithm suitable for real-world IoT environments are the key factors of this proposed mechanism. So this shows the architectural diagram of the proposed study. So as we said, we are dividing this into 4 regions. Formation of smart city region. So as we said, the network structure here, the IoT network is divided into multiple smart city regions, each with an access point. managing a group of homogeneous devices. So here we have IoT devices and the access points, where these regions, this SCR, it has multiple regions where each region is having homogeneous devices. So when I put together, there can be multiple regions with heterogeneous devices. So in each region, the communication is happening with an access point. All access point communicate with a gateway node, which facilitates network management and communication across regions. The nodes in this proposed method are identified as three types. We have normal IoT devices, defective devices, and adversary devices. Normal devices, so here they perform regular sensing and data forwarding tasks. So the job assigned to these devices are done as expected. Whereas in case of defected devices, these devices may act malfunction due to environment factors, but basically are not malicious. The third type, adversary devices, they actively attempt to disrupt the network by launching attacks and moving across the smart city region with spoofed identities. So they are specifically used for introduction of errors or introducing attacks. Next, coming to the trust computation, the probability model towards secure communication. So here we have the trust computation. So how is this trust computed? The model evaluates the trustworthiness of each device by analyzing its behavior. So here we have the factors like the data forwarding represented as DF and data dropping represented as DD. So here data forwarding refers to the number of packets that are successfully forwarded by the device. Data dropping, it refers to the number of packets that are dropped by the device. So here, given this, the trust computation is done. So here, the trust calculated can be a positive trust or it can be a negative trust. So uncertain trust using dot product of network coefficients. So here the trust computation is obtained by an equation where we have the positive trust computation, which is done by the ratio of number of packets successfully forwarded to the total number of packets handled by the node. Whereas mm, uh, the negative trust, it is computed as the ratio of total number of packets dropped to the total number of packets handled by the node. We also have an uncertain trust where this is calculated using the dot product of network coefficients when the number of packet forwarded is equal to the number of packet dropped. Detection of adversaries. If the uncertain trust value decreases, it confirms that the device is an adversary. So, so that is how the trust computation is done. Then we have one more component as allocation of rewards or penalties. So coming to this, we have the proposed mechanism here uses reward and penalty system. So the approach here is the devices will receive awards or penalties based on their behavior in the network. This ensures that adversary devices are identified and penalized. For example, we have normal devices will receive a reward for forwarding data and reporting adversaries. Okay, so where as well as we have the adversary devices are penalized for malicious actions like launching of attacks or migrating to different SCRs. That is the reason. The parameters considered here are again, we have the DF, the DD, as well as we have UA, where UA stands for updating attack information, and RM represents the region migration. The function used for calculating the reward penalty for a normal device includes these three parameters. And the function used for calculating the reward penalty of adversary, it considers these three components. So here we have the devices are empirically assigned profits and resource variables, and based on the observed actions, appropriate rewards or penalties are applied. So here we have one simple scenario of allocation of reward and penalty. So the proposed system uses two variables called as profit and resource. The profit for executing RM is represented as I1. Profit for executing data forwarding is given as I2. Profit for executing or reporting of attacks is given as I3. Similarly, resources used for data forwarding or data dropping as I4. Resources for forwarding as I5. Resources for informing about the attack reporting is I6, resources for region migration is I7, and outlier detection as I8 by the normal mode. So the table here gives us an example scenario of how the reward and penalties are assigned for a combination of target nodes which are adversary, and here it shows a combination of nodes in case of normal scenario. Next, coming to the last component of the architecture, we have reinforcement learning model. So this reinforcement learning model, it makes use of the reinforcement agent, which is trained to recognize normal behavior patterns and deviations to allow it to detect attacks. State representations, the RL models or the reinforcement models can reduce complex IoT data into more manageable representation for decision making. The RL agent chooses actions such as blocking suspicious devices, alerting administrations, or isolating of traffics. The reward design, again, the agent is rewarded for taking actions that prevents the attack and minimize false positives. Benefits of this model here, it reduces computational complexity. The model minimizes the computational resources required for threat detection, and also it quickly adopts and identifies new forms of adversaries in real time. So this proposed architecture was implemented through a simulation setup on MATLAB, where the setup included of 500 devices, 500 IoT devices simulated on 1000 cross 1000 meter square area, where out of this 500 devices, we have 460 devices which are normal devices and 40 devices are the adversary devices. The implementation was set up on a testbed of MATLAB, and the AI algorithms were compared with the cryptographic models. The performance of these models were evaluated based on various metrics such as accuracy as well as execution time and delay. So the proposed model achieves a detection accuracy of 98.4%, and the execution duration, the proposed model reduces execution time compared to machine learning, deep learning, and cryptographic methods. Also, the throughput and delay, there is an improved throughput and reduced delay, showcasing superior communication performance. These obtained results are tabulated as shown in these diagrams. So here this shows the detection accuracy achieved with the proposed model as well as the existing model. The second diagram B, here it is showing the execution duration of the proposed model. So here it is taking less time compared to that of the existing other models. Similarly, here we have plotted the throughputs in bits per second. Throughput of the proposed mechanism is much higher compared to that of the existing system. And the delays encountered here, there is a very small delay in the proposed model compared to the other existing models. So the proposed model outperforms all other AI models such as machine learning, deep learning, as well as others in case of detection accuracy, throughput, and delay. 98.4% for the proposed model compared to 89.7% for the reinforcement learning model. The proposed model is 32% faster than the existing AI models. The proposed model also shows significant improvement over cryptographic models like AES and elliptic curve cryptography. The throughput is increased by 43% compared to the advanced encryption standards, and the delay is reduced by 98% compared to AES and elliptic curve cryptography. To finally summarize the conclusion, the proposed model the proposed AI-based probability model effectively detects unknown adversaries in IoT networks. So the major contributions here are 68% improvement in detection accuracy, 32% faster execution compared to existing models, 98% reduction in delay, 18% enhancement in throughput. And the work can be further enhanced by optimization for more complex IoT environments and extend the model to deal with more advanced AI-based cyber threats. The references used for the proposed work are listed as this. So we thank you all for your, we thank you.